Okay, in this video we're going to look at carbonyls. Now carbonyls, or the carbonyl bond, is a C-O-O bond, so that we call the carbonyl. And there are two types of carbonyls we look at. They are ketones, such as propanone, where in a carbon chain, I'll put a CH3s on to make it easier. Let's do it like that. We've got 3 carbons, and the carbonyl bond is just here, it's in the centre. And we have aldehydes. We'll do similar, where our carbonyl bond is there. And this time it's on the N carbon. So the differences are ketone, general formula, has a carbon in the carbon with a carbon. The carbon in the carbonyl is bonded to a carbon this way and a carbon that way. In an aldehyde, the carbon in the carbonyl is bonded to a carbon that way, but a hydrogen that way. General formula is just like that. Now, another compound that people often think is a carbonyl is carboxylic acids. And that's because they have that group, and this looks like a carbonyl. But an acid gives away its hydrogen, and the bond actually is shared between the two with a negative there. So this isn't quite a carbonyl. So when we talk about carbonyl chemistries, we don't include carboxylic acids. We're just going to look at ketones and aldehydes. The first thing we're going to do is, how do we form these? And we form them from alcohols. So this first one here, this is our propanol. This is a primary alcohol. This O in brackets, this means I'm adding an oxidizing agent. I'm actually going to use a different way to express these. So this, CH3, CH2, CH2OH, so that's propanol, plus my oxidizing agent is going to form my aldehyde plus water. And similarly to that, I'm going to take an alcohol where the alcohol group is on a central carbon, and when I oxidize that, it's going to form my ketone. Now this oxidizing agent, it's a good one to remember, in this reaction it's generally an acid or acidified dichromate ion, sometimes potassium dichromate, but it's acidified with dichromate. And if we add these to our alcohol, our primary, so this is a primary alcohol, or our secondary alcohol, they will form an aldehyde if it's a primary, and a ketone if it's a secondary alcohol. Now the primary alcohol can carry on going if we heated up and added this dichromate as well, and that could carry on oxidizing, lose this hydrogen, that becomes an OH then instead, and it becomes a carboxylic acid. This ketone, once it gets to this stage, we can't add any more oxygens on essentially to this carbon, so that's stopped there and won't carry on. These are known as oxidation reactions. They form our alcohols. Now if we wanted to go the other way, we call this reduction. So this time let's put in my aldehyde. and we're going to reduce this. So I'm going to add a reducing agent, which is represented here by a H in brackets. Excuse me. So this H in brackets, so we're going to need 2 of these. This H in brackets is normally, put it down here, sodium borohydrate, NaBH4. So when we reduce, we're going to go from our aldehyde and it's going to go back to our alcohol. So that is going to go to CH3, CH2, CH2, OH. We see that should balance. This is why we need 2 in front of this H, because we had 3, 5, 6 hydrogens there, and in the alcohol we've got 3, 5, 7, 8 hydrogens. We've got 1 oxygen, and 3 carbons, so it balances. A ketone does exactly the same thing. We had our sodium borohydrate, our reducing agent, and that is going to go back to the alcohol that it was. So on that central carbon we have our alcohol group joining, and this is reduction reactions. Now this has a mechanism we need to learn. So we have our CH3, CH2, and that's bonded to our aldehyde. We'll do it for an aldehyde first. So what we have first of all is a dipole. Oxygen, very electronegative, withdraws the electron mass from this, that's a really wrong word to use, electron density from this bond gets pulled towards the oxygen, making it slightly negative. Because this is having electrons pulled away from it, becomes slightly positive. And when we have sodium borohydrate, we form a H- ion. It's an important ion, the H-. It's a hydrogen that's gained an electron, and that's represented by the fact it's now got 2 electrons, or a lone pair of electrons. This is going to attack that carbon. When it does, pi bond in the CO breaks, goes into the oxygen. So a lone pair of electrons goes towards the oxygen. This lone pair goes in and forms a bond with the carbon, and that forms our intermediate which has a single bond oxygen, it's now negative, with, it had 2 lone pairs before, it's now going to get another one, so 3. Often you'll see it just drawn, and you can get away with just drawing it with 2 lone pairs. We're going to have the hydrogen we had initially, and then the hydrogen we've added on. You see here we had just a single negative charge, this had no charge, here we've got a negative charge. Now, because these reactions take place in water, we'll then have a water molecule, which from AS work we'll know is delta pluses and delta minuses. This negative ion is going, this lone pair is going to grab the hydrogen, and the lone pair from there is going to go back in the oxygen, which is going to give us our final product, which is then our oxygens become an alcohol, and we have our carbon bonded to 2 hydrogens, and that is our primary alcohol back again. Ketones, exactly the same. We go with our propanone. CH3 that way, CH3 that way. Same as last time, delta plus delta minus on the carbon and the oxygen. We'll have our H minus come along. It's going to attack there. Lone pair goes into the oxygen to keep it consistent with black. So our O minus is getting that extra lone pair. We'll have a H on and a CH3. Water molecules always floating around everywhere. Delta plus, delta minus, delta plus. Important to have the dipoles on here because we want to show that why the oxygen is going to attack this hydrogen. So curly arrow to the hydrogen. This goes into that oxygen to give us CH3C OH H CH3, which is quickly that compound. I keep forgetting, didn't add that on the last one. I'm going to have a OH minus as well. So that shows that being reduced. This is our secondary alcohol that's been formed and shows the addition of this, which is our nucleophile. So this mechanism is nucleophilic addition. It's not substitution because we're not swapping anything off. Something's just getting added on. So we're adding to the initial molecule without anything coming off it. So it's an addition, and this negative, it's a lone pair donator. It's going to give that to form a bond. So it's a nucleophile. Easily spotted because it's either a lone pair or a negative charge. So we can do nucleophilic addition with other compounds, such as the CN minus ion. So the CN minus ion, let's add it to just a small aldehyde. So delta plus, delta minus, always important to start. This time we'll have our nucleophile on there, CN minus, and that attacks the carbon. Negative going to positive. That bond's going to break to give our intermediate. It's taken the electrons from that bond, so it has that extra lone pair. We'll have our hydrogen and our CN bonded to that carbon. We've got our water then, delta plus, delta minus, delta plus, and that lone pair is going to get donated to the hydrogen, or they're going to come together to form a bond with that lone pair of electrons. The electrons in that bond are going to go into the oxygen, which is going to give us CH3, C, OH, CN, H, plus OH minus. And that's nucleophilic addition, nucleophile here, getting added on. So it's getting added on, nothing's getting swapped off that carbon, it's just adding more stuff onto it. Final thing we need to look at is the test for carbonyls. So we've got, first of all, test for carbonyls is 2,4-DNPH, or dinitrophenylhydrazine. Now if we add 2,4-DNPH, don't need to learn dinitrophenylhydrazine. If you do, fantastic, but 2,4-DNPH for all carbonyls, both ketones and aldehydes. This forms an orange precipitate. So it's an orange solution anyway, 2,4-dinitrophenylhydrazine, but on addition to a carbonyl, you'll get an orange precipitate. Now, if you added this to carboxylic acid, it doesn't form the orange precipitate, which is why we know it doesn't act like a carbonyl. And any other compound, in fact, won't react with the orange precipitate. Now, we can identify then with this test a ketone and aldehyde. If we wanted to identify whether we had then a ketone or an aldehyde, we do Tollens reagent. And ketones don't react. Aldehydes form a silver mirror, unless I've done the practical, in which case you'd see nothing because I'm useless. But the aldehydes will react with this to form a silver mirror, ketones don't. So we can use this to identify which carbonyl we have. First of all, if we have a carbonyl, so if we're added D24DMPH and we've got an orange precipitate, we know we've either got a ketone or aldehyde. If we then add Tollens reagent and do the silver mirror test, and it doesn't react, it's a ketone. If it produces a silver mirror, it's an aldehyde. And that is carbonyl chemistry.